Howdy! In this mini lecture, we will continue to discuss new renewable energy alternatives to fossil fuels. Specifically, we will discuss geothermal energy, wave and tidal energy, and hydrogen fuel cells. The student learning objectives of this mini lecture are: describe geothermal energy and the ways we make use of it, and assess its advantages and disadvantages, describe ocean energy sources and how we can harness them, and explain hydrogen fuel cells and assess the advantages and disadvantages of hydrogen fuel. The third new renewable energy we will examine is geothermal energy. Geothermal energy is thermal energy from beneath Earth's surface. This type of energy is generated from the radioactive decay of elements under high pressures deep inside the planet. The heat rises to the surface of the Earth through magma, fissures, and cracks. When this energy heats groundwater, the water may erupt at the surface as geysers or submarine hydrothermal vents. Geothermal energy can be used to heat water, which in turn can be used to heat buildings. Geothermal is actually very efficient because it is using natural means to heat water. Geothermal energy can be used to heat homes, buildings, or greenhouses, to drive industrial processes, to dry crops, or to generate electricity through the use of a geothermal power plant. 90% of Iceland is heated through direct heating with piped hot water warmed through geothermal energy. As you can see from the map in the upper right-hand corner of this slide, heated groundwater is geographically determined. The U.S. is a leader in geothermal power. The largest geothermal power plants are the geysers in California, which provide electricity for 750,000 homes. Globally, one-third of the geothermal energy we use is for electricity and two-thirds is for direct heating. Although heated groundwater is available only in certain geographic regions, we can take advantage of natural temperature differences between the soil and air anywhere through the use of ground source heat pumps, or GSHPs. GSHPs take advantage of the fact that soil temperatures vary less than air temperatures. In winter, heat is transferred from the ground to the buildings through the use of a GSHP. In summer, heat is transferred from the building to the ground. Compared to conventional electric heating and cooling, GSHP are 50 to 70% more efficient at heating spaces, and they are 25 to 40% more efficient at cooling spaces. GSHP can cut electricity use by 25 to 60% and can reduce emissions by up to 70%. The advantages of geothermal energy are that it reduces emissions and that it can be sustainable if the groundwater is not withdrawn faster than it can be recharged. The disadvantages of geothermal energy are that patterns of geothermal activity in the crust shift, meaning geothermal hotspots may change. It is limited to areas where the energy can be tapped, and dissolved salts and minerals corrode equipment. One method being developed to overcome the geographic limitation of geothermal energy is enhanced geothermal systems, or EGS. With EGS, engineers drill deep into the rock to fracture the rock and pump in cold water. When the water is heated, it is withdrawn to generate electricity. In theory, EGS could be used in many locations. However, EGS also appears to trigger minor earthquakes, so for now, our use of geothermal power will stay localized to areas where geothermal energy is naturally occurring. The next new renewable energy alternative we will consider is energy we can harness from the ocean. There are 4 different approaches to obtain energy from the ocean. 3 of the 4 approaches involve ocean movement, simplistically capturing the kinetic energy in ocean movement and converting to electrical power. The other approach that involves the ocean but not its movement is based off of temperature. The first developing technology aimed at harnessing energy from the ocean we will consider is wave energy. Wave energy is energy harnessed from the motion of ocean waves. Many designs for machinery to harness wave energy have been developed, however few of these designs have been adequately tested. 2 designs are shown in this slide. In the image in the top right, you see an offshore snake-like wave energy converter. Machinery and hydraulic fluids inside the converter use wave motion to generate electricity, which is then transmitted to shore using undersea cables. The image in the lower portion of the slide shows a coastal onshore facility. This facility captures the energy from waves coming to shore by funneling the waves into a narrow chamber. The rise and fall of the water level inside the chamber compresses and decompresses air. This causes air to flow through the chamber. The airflow drives a turbine on the outside of the chamber to generate electricity. Currently, there are no commercially operating wave energy facilities either offshore or onshore. There are only demonstration and research projects at the moment. The second approach to harnessing energy from the ocean's motion is to capture tidal energy by building a dam across the outlet of a tidal basin. Differences in height between low and high tide are greatest in long, narrow bays. The incoming tide flows through the sluice gates. The sluice gate is closed and the tide recedes, causing there to be a difference in the water level on either side of the barrage. When the sluice gate is open again, the outgoing water leaves the basin and in the process turns the turbine to generate electricity. In short, tidal currents turn turbines to generate electricity. The largest tidal station is in South Korea and is the station shown in this slide. There is also a 50-year tidal station in France, which is just slightly smaller than the one in South Korea. Small stations operate in Canada, China, Russia, the US, and the United Kingdom. A third way to harness marine kinetic energy is to capture the motion of ocean currents, such as the Gulf Stream. Devices that look like underwater windmills have been erected in European waters to test this idea. This approach is so new and novel that it is difficult to find anything other than artist renditions of the underwater turbines. Such an image is seen in the upper portion of this slide. Needless to say, tapping into ocean current energy is going to require a great deal more research and development before it is ready for commercial power generation. The final approach we will consider for harnessing energy from the ocean is ocean thermal energy conversion, or OTEC. This approach uses the temperature difference between the surface of the ocean water and deep ocean water. To grasp the potential scale of OTEC, consider that each day tropical oceans absorb solar radiation equal to the heat content of 250 billion barrels of oil. There are two approaches to OTEC. The first is a closed cycle approach, which pipes warm water into a facility that evaporate chemicals, such as ammonia, that boil at low temperatures. The evaporated gases then spin turbines to generate electricity. Alternatively, an open cycle approach pipes in warm surface water into a vacuum. The steam from the warm water is then used to spin turbines for energy. The added benefit of this approach is that the water that evaporates can be recovered, condensed, and sold as desalinated fresh water for drinking or agriculture. As with all ocean energy approaches except tidal energy, OTEC is still in development because costs are still too high to create a commercial facility. The next new renewable energy alternative we will consider is hydrogen fuel. Hydrogen is the world's simplest and most abundant element. What you should understand about hydrogen is that it is an energy carrier, not a primary energy source. Hydrogen fuel cells have the potential to store large amounts of energy cleanly, conveniently, and efficiently. The energy that is carried by hydrogen fuel cells can then be converted and used as an energy source at later times and in different places. The tricky part about hydrogen as a fuel source is that hydrogen gas does not tend to exist freely on Earth. Rather, hydrogen atoms bind to other molecules. Energy, therefore, is needed to force molecules to release the hydrogen. Scientists are studying several ways to produce hydrogen. One of the most common methods for releasing hydrogen from bonds is electrolysis. In electrolysis, electricity is used to separate hydrogen from water molecules. You can see the equation for electrolysis in this slide. Specifically, two water molecules split through electrolysis yields two hydrogen atoms and one oxygen atom. The image in this slide illustrates the process of electrolysis. Hydrogen production's impact depends on two things: the source of electricity used in electrolysis and the hydrogen source. If electricity is produced from renewable sources such as solar or wind, then the hydrogen produced would be very clean. Whereas if the electricity used for electrolysis is from a fossil fuel, this will create greenhouse gases and further deplete our low stocks of these limited fuels. In this slide, you can see the chemical equation for using methane to split hydrogen from water. The products of this reaction are 4 hydrogen molecules and 1 carbon dioxide molecule. In order for electrolysis and hydrogen fuel cells to be sustainable, we must find ways of splitting hydrogen without using fossil fuels. Once isolated, the hydrogen fuel can drive electricity generation in a hydrogen fuel cell. The chemical reaction to generate electricity in a fuel cell is simply the reverse of electrolysis. An oxygen molecule and 2 hydrogen molecules bind to form 2 water molecules. When this process takes place in a fuel cell, it generates electricity. In this slide, you see a diagram of a hydrogen fuel cell. In a fuel cell, atoms of hydrogen are split into protons and electrons. The protons, which are the hydrogen cations, pass through a proton exchange membrane. The electrons, meanwhile, move from a negative electrode to a positive electrode via an external circuit. This external circuit is a loop of wire outside the fuel cell with a little light bulb next to it. The movement of these electrons generates a current and electricity. In the final chamber, the protons and the electrons combine with oxygen to form water molecules. The take-home point from this figure is that the input into a fuel cell is hydrogen atoms in the form of H2 and oxygen, and the output is water and electricity. These types of cells could produce electricity to power cars, homes, computers, and other devices for which we need energy. Hydrogen fuel cells are currently being used in some places. However, we lack the infrastructure to implement this fuel on a large scale at this point. The benefits of hydrogen as a source of fuel are that it produces few greenhouse gases and pollutants depending on the source of energy for electrolysis. If kept under pressure, hydrogen is as safe as gasoline in fuel tanks. Hydrogen fuel cells are energy efficient. Depending on the technology used, up to 90% of the energy released by the reaction can be used. They are silent and non-polluting. Hydrogen is the most abundant element in the universe, so as far as we know, we will not run out of it. And hydrogen as an energy source can be clean and non-toxic. The costs of hydrogen as a source of fuel are that we currently lack the infrastructure in our established cities to fully utilize hydrogen as a fuel source, so we will need a great deal of investment in infrastructure to accommodate the switch to a hydrogen economy. We must build the facilities to transport, store, and provide the hydrogen fuel. Some research suggests that if hydrogen leaks from the areas we produce, store, and transport it, this could deplete stratospheric ozone and lengthen the residence time of methane in the atmosphere. Finally, if hydrogen is not stored under pressure, it can catch fire and explode. While this sounds alarming, remember that gasoline can also catch fire and cause explosions if not stored, handled, and used properly. That concludes this mini lecture on new renewable energy alternatives. Please review the weekly outline and complete the activities for this week per the schedule set forth in the outline. Thanks and gig 'em!